All right. Well, thanks for being here today. It's good to see you. How's it going? How was the finite element? Did it work out okay? Yeah, all right. I think there still might be some issues with coordinates and stuff, but at least you should have been able to figure out like an S23, an S13, or S12, or actually an E12, E13, E23. That would have given you what you predicted. And it's nice, you know, it's all open source. When you take multi-physics simulations, which I enjoy teaching, I got to teach it for the first time last semester. We'll do ANSYS, we'll use ANSYS, but you'll see the kind of parallels and the processes, okay? Today, we've got kind of an abbreviated session, and the assigned problems are not many, but these are particularly difficult, I'd say. So I'll show you the whole where we've kind of outlined how to solve them, okay? They're not in the slides, or the problems are in the slides, but I'll show you where you can find some assistance, right? I'm glad that people are starting to communicate some in the group me, all right? Yeah, if you are having a question, there's a good chance someone else is having a question, okay? So please, it's great to see when you like answer each other's questions. You know, and then if you don't get a response, then please feel free to send me a message in the Canvas inbox, and I'll get to it. All right. So today we're going to talk about drawing shear force and bending moment diagrams, and we already kind of did this last time, so it'll be a little bit of a review, but in a little bit more detail. And then whether or not we get to it in the next 30 minutes or so, session 13 is going to be about calculating bending moments and doing some derivations for how we can figure out, sorry, I said bending moments, but how to go from bending moments to bending stresses, okay? So after today, you'll have a rough idea of how to calculate stresses, not in this session, but in the next session that we'll do, so between session 12 and 13, you have a good idea of how to calculate stresses in beams, which means you kind of complete the triumvirate of bars, shafts, and beams, okay, in terms of being able to determine whether or not they're going to fail. And then what we're going to do from there are some other scenarios and some combinations of the types of loadings that you see with these structures. So last time we talked about dv dx is equal to w, and we talked about dm dx is equal to v. And I saw in the group me that maybe one of the multiple choice questions, there was an error, so I need to go back and take a look at that. But these are the appropriate relationships. Okay. And then we talked about this yesterday as well. This is about, like I said, there are the three pillars in mechanical problems. We have the equilibrium, the geometric compatibility, and the constitutive relationships. But this particular approach is focusing mostly on just equilibrium, and equilibrium with respect to the external loads and equilibrium to what's happening inside. Okay. So the first step here by CDL, Crandall, Dahl, and Lardner, is to create a model. And then the second step, as we discussed, is to go ahead and calculate the external equilibrium, right? And this is kind of, this step 2 is kind of like that step 1 that we discussed earlier. First do the external equilibrium. It was kind of assumed that you would create a model, okay? And then after you've gotten the external equilibrium completed, right? And these slides are identical to what we had yesterday, or this slide is identical. Okay, then what we do is we go ahead and we look at the internal equilibrium. Okay, and typically for beams, it's method of sections. We don't really think about method of joints too much here. So moving forward, all right, we talked last time, okay, about how we could handle looking at a distributed load on a cantilever beam. Okay. And we talked about using external equilibrium, right? And we talked about looking at internal equilibrium. Okay? And this is the way you would do things in statics, right? So you could have completely done this at the start of the course, right? And then drawing these out. And this is still an important skill to have, right? This is just like really fast animation of the process. But we talked about how you're going to want to select a location for the moment. We talked about how, you know, it doesn't matter so much about where you pick, where your forces might be. We talked about how the external forces, so anytime I write an R, right, MR or R there, right, that means that it's an external force and you can kind of pick and choose the direction of those. But anytime you're dealing with the internal ones, like the shear force V or M, those are going to be following the convention. All right, so we talked about this, and same convention you used last semester if you used Hibbeler's book. We're still using Hibbeler's techniques. Okay, so now this question, all right, is asking us to find a maximum. So how do you typically go about, you know, before you do anything about mechanics, what do you do to find a maximum? Yes?
Like derivatives, you see what it's equal to do.
That's right, right? So if we're trying to find the maximum bending moment along a beam, okay, we would likely take the derivative of the bending moment. Okay? And then we set that equal to 0. What's the derivative of the bending moment?
Shear force.
Yeah, the mdx is equal to v, okay? So now we start to see something useful that comes out of these shear force and bending moment diagrams. Okay, so we want to be able to, yes, use equilibrium, but in the end, okay, we're going to be thinking about a graph of shear force when it crosses 0, okay, and then try to see if we can figure out the appropriate maximum bending moment, okay, and so to kind of look at this, okay, all right, we're going to take the derivative of the moment as a function of position, right, and that would be the shear force, right. So as we kind of approach this problem, okay, let's do now the kind of 3 things that CDL suggests. 1, we create the problem, okay, so it was created for you, and the second is performing external equilibrium. Okay. What's kind of interesting, right, with the dV dx is equal to W, we mentioned this yesterday, but dV dx equal to W is kind of this interesting formula that relates an external load to an internal force. And a lot of times the equations that we have, they don't, you know, we're talking about internals, right? But when you do method of sections, you know, that's intrinsically relating the external, right? Because you cover up part of it, and then you look at the externals, and then you look at the internals, and that relates them to each other as well. But external equilibrium, and at this location, we have the effective force, right? So above the O here, we have the effective force. That is just going to be the distributed force, right, which has units of newtons per meter or force per length, okay, times its length, and its length is L over 2. So then it ends up being W naught L over 2. And of course, maybe not of course, but it's acting halfway across. Again, you've seen this before, we've talked about it. These external forces R1 and R2, okay, we could draw those the other direction. I wouldn't, okay, because they would end up being negative, but you could. So then, this problem ends up being a homework problem, all right, and that's that. But let me show you where you can get some advice, okay. So if you go to the website, and I think I misnumbered something, Beams 1. But anyway, we're in Beams 2 now. Again, it's session 12. If you come down here,
Can't see the.
oh, what happened? Oh, okay, thank you for letting me know that. That's wild. And not cool. Let me see. Okay. Thank you. So, coming back, right, you go to the website and we're in session, I think this is 12. Yeah, session 12. And if you go down now and you look, I haven't been doing it this semester so much, okay, but if you see here, we have this in-class and office hour notes. There were so many questions in the past, or last fall, that we were able to, well anyway, I keep a track of them on this OneNote file. So if you come into session 12, so you open up that file, you come into session 12, you will find some very helpful information, okay, in terms of how to attack these problems. And I'll leave it at that. And if you have other questions, feel free to call me, or feel free to contact me through Canvas or group me. All right. We're gonna go on though, but the thing to learn, or the thing to keep in mind there, as we said previously, whoopsie, where is it? Yes. The thing to keep in mind in this problem, okay, is, whoops, and there's a lot of information there, okay. There you go. If you stop that video, you might have some helpers. The thing to keep in mind is that the derivative of the moment, okay, as a function of position, means that we're looking at when the shear force crosses 0. Okay, so going on, that's kind of the way we did it in statics. Yesterday we talked about how we go forward using dv dx equals w and dm dx is equal to v. Right, so these are the two equations. And we are going to first still calculate the external load, and then we are going to look at the ends of the beams. So looking at the boundary conditions and how they relate to the internal shear force and the internal bending moment at the ends. And then we will go ahead and use the differential and integral forms for the distributed load, for the and then after the distributed load, then we'll look at dm dx, right? And if the distributed load is, if there's no distributed load, that's nice, okay? That's nice. But in addition to distributed, so you could have distributed load equal to 0, right? But we still have to satisfy the boundary conditions, okay? So distributed load equal to 0 means that, okay, I've got like a flat constant, right? And so then I have to satisfy the boundary conditions. But when I satisfy the boundary conditions, if there's a concentrated moment, for example, applied somewhere, like in MechMat, right? Or if there's a concentrated force applied somewhere, it's very possible that, you know, it's not just going to be flat right across. You can have a discontinuity. So we want to keep those things in mind. Now, or it could be something where you have no distributed load over part of it, right? And then suddenly the distributed load is acting like halfway across, like the problem that we were just looking at. Okay, so there are lots of variations. So just be careful, or you know, that first equation is still important, okay? And you want to make sure that you put in the appropriate boundary conditions and that you're looking at the appropriate scope. So we kind of did this a little bit yesterday. We did it a lot, okay? And we talked about how we could go from the quadratic, right? And then moving up one, if you take the derivative of this, right, of second order, then you get a first order. And if you take the derivative of a first order, you get a constant. And that's what you see happens here. and there's a negative slope here for the internal shear force, and that corresponds to a negative constant, right? So whatever m was, it's negative, and well, we know that m, that slope, for example, if it was mx plus b, that slope now is reflected in the w naught. So w naught is going to have a negative quantity. The integral form, right, is to go the other direction. So often I think it is easier, or often you're going to do this, because I will probably draw a diagram for you and not a bending moment diagram, right? I mean, it's like a physical system diagram, okay? Because we live in a physical world. So in this case, using the integral form of these relationships allows us to go from the actual geometry with the loading on it to figure out what's going on inside. And for anyone who thinks that, you know, mechanical engineers just think about tangible objects, no, we don't. We definitely more abstract, and we now have. Well, I guess I'll show a little bit more of this, but essentially you have almost like this super power vision where you can look at a table, you can look at some type of structure and begin to think of, oh, hey, what are the stresses? Where's the stress constant? Where's the highest stress? You know, where's this thing gonna fail? What's the distribution of the forces? Right? It's like a superpower. So we do think about abstract and invisible things as well. The other day, I was waiting for the bus, and I was at the New Brunswick train station. Has anyone looked at the cables that run across and how high they are? And the steel beams that are like going up vertically, they go up probably 50 feet. Like straight up, and all it is this cross section. I'm like, wow, that is so incredible. How does this thing not buckle? And then you look at, I think, what are tensioning cables going across? Like, yes, there is power traveling between them, right? But there's no power. Well, I don't know exactly how they've got it all set up, but they're going up, and I'm like, gosh, some of those have to be just straight up supports. And it's almost like they created a suspension bridge, but not quite a suspension bridge between these trusses. Like, oh, Marissa's not here. Our civil engineer is not here to glory in this. All right, but yeah, you get this superpower. You get this superpower where you can look at a system and kind of have an idea of what's going on internally. So the methodology here, it's always like, not always. I don't like superlatives, okay? But, and my kids will tell you that I'm kind of a punk sometimes. I'm like, is that really true? Can you always feel that way? Or can you always think that way? Or, but anyway, or never, right? But anyway, so I digress. You're interested here in first calculating external loads, looking at shear forces at the ends of the beams, calculating the moments at the end of the beams. So that is essentially identical to what we would normally have done. Okay? Or what is normal? What we would have done with the differential form, I guess. But this is the integral form, so it's kind of repetitive to say that. But it's what you would have probably done in the old ways of doing things too. Okay. Which is the statics. Right? And then we're going to use the differential and integral forms of distributed load, shear force relationship. So make a shear diagram. And so I guess we're going to draw it out. Okay. And there's the F effective. There's the W naught O. There's the reaction moment at A. Okay. And then we've got our reaction force, W naught L. And we can look at the left end. All right, so this is all for this. And look at the right end. And we did some of this yesterday. Here's the, okay, almost there. Almost to the right end. Okay. But it just to pause on this for a minute. This is abstract a little bit in that are you really all the way on the right end? Like, how close am I drawing this? I'm drawing a little sliver, but I am essentially saying that I'm all on the right end. And so the forces and the moments are going to essentially balance out whatever the external reactions are there. Okay. And these are 0 here, and then above, right, we had an R and an NA. Make sure we get the arrows, the conventions correct. Then we can do the integral of the distributed force with respect to x, and in this case W naught is negative, so we'll go ahead and put a negative sign in there. And we have a constant, it's indeterminate, not indeterminate, it's integral plus C1. And indefinite, sorry, integral. And then we can figure out the W naught L and plot it here. And we know that on the right end, V of L was equal to 0, so that's going to be down here. Okay. And we integrate this equation right here, or this equation with that constant, and then we get the quadratic formula, or the quadratic terms. Quadratic term, this term, and then a new constant, which has to satisfy what? Well, we plug in 0, right? And, well, we plugged in 0 for the shear force up here, and we that wasn't particularly helpful in telling us what C1 is, so we had to plug in this one, L, and then that was helpful in telling us what C1 is. And here, okay, we can, since we can, if we plug in 0, or sorry, if we plug in the 0 here, we do have a quantity. So that is, so the m of 0 is helpful for calculating this one out. Okay, and then we have it like that. All right, so question 2, all right, is going to look like this on the homework. And once again, I suggest that. Yes, yes, Kavya.
On the slide before,
Yep.
why is C2 equal to negative naught instead of other than?
Okay, so if I plug in this boundary condition,
Okay.
I'm doing it at 0, right?
Right.
So then this times 0 is 0. This times 0 is 0. And C2 has to equal that.
Okay.
That's why that one is the way that it is. Yeah. Good. I'm glad. Thank you. I'm a little rushed today, if you can't notice. It's not because I'm just trying to, because we got stuff. So anyway, if you are interested in getting a hint, you might want to take a look at, oh, not this one. Yeah, this one. Okay, you might, if you would like a hint. But this one, how do you say it? This is not the trickiest of the set. Okay, definitely not. Yes.
Wait, so how do you know what boundary condition to pick when you're plugging it into the equation?
Okay, good. All right, so I am going too fast. Well, what do you think, Andrew? I think you might have an idea. What I'll say is, oh, go ahead.
I'm not sure. I just know that those two equal 0 and then the other ones
Yeah.
don't. Is that a factor?
Yeah. So I think the Saint Denis principle, KISS, keep it simple, silly, all right, or stupid, whatever you want to say. Both of these boundary conditions have to be satisfied for V, for example. Like this V of L and this V of 0, right? you have two boundary conditions per equation, and they both have to be satisfied. Okay? So I'm a lazy person. If I can satisfy it by plugging in 0, right, and that becomes 0, that's the one I want to choose. Okay? So that's how I'm going to try to keep it simple. So that's my first option. My first go-to is plug in this, make this 0, and then see what happens. And in this case, it's good because I have an actual value, and I'm good to go. In a case like this, is also good. I can plug in zeros, right, and then I have a value, and I'm good to go. All right. So I'm gonna first try to see if I can use these to help me out. Okay. And if it's equal to 0, then that means it's equal to 0 too. Every now and then, though, you have like an L minus X term or something here, and like if it's L minus X, then that means the simple thing to do is to plug in L, because then that will be equal to 0. Okay, so that's how you go ahead and do it. This boundary condition, I mean, if you plug it in, it's actually not that bad, right? Because I plug in minus W naught L here, and that's equal to 0. So that means that C1 has to equal the positive version of that, W naught L, right? And that gives you the same thing. Okay, so the boundary conditions have to be satisfied. We're satisfying all these boundary conditions, but I just try to keep it simple, and usually I try to plug in X equals 0 first. Okay, does that make sense? All right. Isaac, you were looking, you're so intent. There's something, did I say something disturbing? Okay. You got it? All right. Good. So, what's next? Well, let's look at the last part, okay, where we talk about or review managing discontinuities. Okay, and what are these two equations based on what we discussed yesterday? Remember? The discontinuities. This is where you have concentrated loads. Yes.
So the delta M equals M applied.
Right. And the delta V equals F applied. Right? And which direction is the M applied? This is key. Remember we said, so which direction do you think it is? Clockwise or counterclockwise? So it's actually clockwise. This is the non-intuitive part of it. Okay, so the MAP, it's important to remember this. Okay, so FAP is as you expect. If it's up, then it's delta V is equal to FAP, right? And we actually derived both of these yesterday, very quickly, but we did. Well, actually, they're not very long derivations, right? You take a slice. So if you forget, you can rederive it right then and there. Okay? But if you have a concentrated moment, okay, this one's actually clockwise, and this ends up being the delta M equal to MF. Going from minus X to positive X. Okay? And when we're going from the left side to the right side in both of these cases. Okay, so that's something to keep in mind. You know, if you draw this going the other direction, then you may want to flip things. Because, you know, why am I saying that? But, you know, if I'm going from this side, right, I went up when I was going for the left, but now I actually go down, right? Because that's a cliche, right? What goes up must come down. No, but if I'm going up as I'm coming from the left, right? Obviously, if I'm going from the right, I've got to go down. And same thing here. At least if I'm coming from the right, I'm going to the left. I'm going to take a step down, unless I flip this direction. Okay. So. we did this derivation yesterday, okay? And so this is just repeating it. Equilibrium, Fy, yeah, we did this. Okay? That was small, and we skip it. Okay? And then when you encounter a concentrated couple moment, all right, the same thing. So this is the derivation, and it's just here again as a reminder. Now, what does a more complicated problem look like? Well, maybe something like this. Now we've got, reaction loads on either end, and we write them out, and we're first going to attack the external loading, okay? And then we're going to look at the values of the left and the right sides. You know, sometimes you don't have to do the values of the left and right side. Like if you just did the values of the left side, you could probably go ahead and solve everything. But what do I mean by solve everything? I mean, because I could just decide I'm going to do, the boundary condition when v of 0 is equal to blah and m of 0 is equal to blah, okay, and that might work out. But when I draw these things across, I usually first draw, the values of the left and the right side on the shear force and the bending moment diagrams, and it's kind of it helps me visualize. Okay, like I gotta get back to this. Like often there's 0, 0, and I gotta get back to them somehow, or I have some forces and I have to make sure I get back to them. Okay, so once again, we're taking the slice, and this is the convection. This is external, so it doesn't really matter. Okay. This may be a little bit counterintuitive. Like I made good choices. All right. Some of this class is about making good choices. What is good? That's very subjective. So maybe not ideal engineering term. Okay. But here you can kind of see that when I shows these external loads, that the bending moment, right? It's going to be like if I take this thing. If I put this box here, right, and I start twisting it, right, you can see that, one side I'm going to be pushing down on, and the other side, actually, I got to hold it down, okay, if I have statics. So you can kind of see that this left side is holding it down, whereas the right side is pushing up against that moment that's being applied. So, now, we finish our external equilibrium, and we keep on looking at the external equilibrium on the right side. And when we do that, we can get an idea of what V is going to be, what M is going to be, right? And we can see that the we have a shear force on the left side, but we have no bending moment on the left side here. And on the right side, we also have no bending moment, and we have a shear force. And that shouldn't be too big a surprise. Why? Because we know that these supports can't provide a moment. These are pins. If it were a wall, it would be a different story. But because it's a pin, they're pinned or roller constraints, there are no moments there. So they're nice. Those are like, I like pin constraints. I like walls too. But yes. Okay, and then what we're going to do is we're going to go to the second step here in this methodology, where we can use our equations for discontinuity. In reality, right, the methodology should be like, step 1, do all this boundary condition, external loading stuff. And then step 2 is really like, okay, apply the dV dx, apply the dm dx, apply the concentrated loading equations, right? So there's really like 4 equations that you want to keep in mind. And these are 2 of the 4 on the left. Okay. So here, what do? we can integrate w dx, but is there any w? No, it's 0, right? So then we get a c1, and c1, all right, is equal to v, and it's good here. V is the same on both sides. That's a good thing, right? Because now I can satisfy that constraint, or I can satisfy the constraints, and I can get the result. What's often a little bit confusing to me is that, wait, there's a discontinuity there. That discontinuity is a discontinuity in the moment, not in the force. So the shear force doesn't care about what's happening in the bending moment. All right, and then we can write this out as such. Now we see that, yes, you have that negative slope, and then we jump up, and then we come back down. Because that slope has to be constant. So the only way to get to satisfy the boundary conditions is to have that jump there. Okay? All right. Yes, Andrew.
So how would this be different if M was going counterclockwise?
Yeah. Oh, that's good. How do you think it would be different?
Would just be a change in sign.
So, yeah, so we know that if it were going the other direction, right, that this would be flipped. Okay? Is that right? Okay. So that would be flipped. I could flip-flop the reaction forces in terms of the directions, but they should still be giving, well, let's make sure we get this right. The V of naught yeah. So here, if I flip this and I flip this, okay, or I just have these be, they're now going to be the negative of whatever they were before, right? So I'd have m naught over L like this instead, right? Then yeah, they're going to have a flip sign. Yeah, so it's going to end up looking. That's a good question. So it's going to end up. So if you flipped, okay, m naught, right? What you got, okay, for the for V, you're going to have this instead, m naught over L, okay, and that comes from the external equilibrium plus the looking at the edges, right? Looking at the left and the right, and then so if it's a positive slope, then and then these still are going to be 0. So then I've got to do this like this, right? Because if I flip the direction of m naught, right, then it's going the other direction, which means I actually have a step down. Okay, because the m at would be negative, or the delta m is going to be negative. Okay. Good. All right. So question 3 is a little bit tricky. Actually, it's a lot of it tricky. All right. But once again, come over here, take a look. That was like the first question they asked in office hours, was how to handle this thing. Okay, this one is particularly difficult in terms of their, how do I say it? The slope of the moment changes. Okay, it doesn't have a discontinuity in the slope, but it doesn't have a discontinuity in the moment, but it has a discontinuity in the derivative of that, right? That's a shear force, which means that it changes its slope. Okay? And it's interesting to see that, okay, this applied moment doesn't affect the shear force, right? Just like we saw here. Okay? But the applied force here does affect the slope of the moment. Okay? So take a look at that, and I think you'll be good to go. So again, right, the goal here is to kind of help us develop a sense of X-ray vision. All right? I don't really have the greatest X-ray vision, but you can imagine that, you know, as a load or something is going across the bridge, the idea is that, you know, maybe you could envision the bending moment or the shear force, okay, diagrams as this load is transversing, and have an idea of what might fail. Okay, so that's session 12. Let me go ahead and I'll listen.